In this video, I will analyze the character table of the D3h point group and then predict the symmetry of the vibration modes of an atomic cluster that belongs to this D3h point group. You can download this Excel spreadsheet from my website, so you can click this link, or you can just search for PCAM CW. So let's try this PCAM CW. The first link is my web page, and if you scroll down, I think it's under this building physical chemistry from scratch. I have those documents for a lot of videos I made, including molecular symmetry videos. You can see a bunch of molecular symmetry here. Some about infrared and Raman activities. Some are about vibrational modes for different molecules, like acetone, like this molecule with a C4V point group, and some other point groups like C2V over here, C3V here, and D4h point group. So today we're looking at D3h point group. Again, you can just click this website and get here and find some of the lecture notes, Excel sheets that I use in the video. Now let's get back to the character table. First, we need to know the symmetry operations. Here's one example. You have 5 atoms with a number of symmetry operations, in total of 12 symmetry operations. You have identity operation. You have 2 C3 operations. That means we can have this atomic cluster or molecule rotate about the principal axis 120 degrees or 240 degrees. That's why you have 2 of those. What about 360? Well, that's just the identity operation. And then 3C2 prime. We have 3 C2 prime symmetry operations. Well, because we have 3 C2 axis perpendicular to the principal rotational axis. Alright, so I'm going to show you one of the 3. It crosses this atom and the midpoint of this 2. And you can see this C2 axis is perpendicular to the principal rotational axis, and also this C2 axis bisects this triangle. Alright, you have 3 of those because the 3 C2 axis cross one of the 3 atoms. And when you do C2 operation, it's just 180. We have sigma h, which is perpendicular to the principal rotation axis. So this 3 atoms can define a plane, and that plane is the sigma h plane in this molecule. We have S3, improper rotations. Improper rotations are the rotations about the principal rotational axis followed by a reflection. So over here we can see this is the principal rotational axis. You can rotate the entire structure 180 degrees or 240 degrees, followed by a reflection with respect to the sigma h plane. Alright, so that's we have 2 of those, because 120 240 degrees. And then we have 3 sigma v's, y3. Well, so one of the 3 sigma v symmetry planes contains 1, 2, 3 atoms. The second one, 1, 2, 3. These 3 atoms define a second symmetry plane, and these 3 atoms define a third sigma v symmetry plane. So we have a total of 12 different symmetry operations. Therefore, the order of the D3h point group is 12. Another way to calculate the order is you can square this column. 112, 112 under the identity operation, you get 114, 114. You sum it up, you get 12. So these numbers are simply this column squared. Now let's look at the vibrational modes. Step number 1, we need to determine the number of atoms that remain in their original positions after a symmetry operation. So this is under the identity operation E. So you can see E over here. And if you do nothing, you have all 5 atoms remain in original positions. So you put 5 here. C3, rotation. After the rotation about the principal rotational axis, only 2 atoms, only these 2 atoms remain in the original position. This one on the left, this one on the right, so you put 2 here. So this number is under the C2 rotational operation. Alright, so if you rotate this entire structure 180 degrees about this axis, only this atom remains in the original position. Over here, sigma H contains these 3 atoms. So when you do a reflection with respect to the sigma H symmetry plane, these 3 atoms remain in their original positions. These 2 atoms will switch their positions. They move. And this 0 is under this S3, improper rotation. So when you do improper rotation, you rotate and then reflect. Alright, so after you rotate, these 3 atoms will change their positions and followed by a reflection, and then these 2 atoms will switch their positions. So that's why you have 0 here. Finally, sigma V. There are 3 sigma V symmetry planes. They all contain the principal rotational axis. And each sigma V symmetry plane contains 3 atoms. For example, 1, 2, 3. We're going to do a reflection, and then these 2 atoms will exchange their positions. So you put 3 here. Alright, this is just step number 1. Step number 2, you get the characters of X, Y, and Z. This is pretty easy. If you click here, B6 plus B8. If you click here, E6 plus E8, or G6 plus G8. So you can see row 6. That's all those 6 numbers are the characters of X and Y, and row 8 over here, these 6 numbers are the characters for Z. So you need to sum it up, and then you get the characters for X, Y, and Z. So now you have actually all those atoms that remain in their original positions after the symmetry operation multiplied by the characters of X, Y, and Z. So that means they remain in their original positions, and we're looking at their motions as well, X, Y, and Z. We do a multiplication here, this 2, alright, and this 2, and this 2. We're not done yet because you can see 1, 2, 3, 6, 5, 6. These 6 numbers correspond to the 6 columns here. Alright, each column is one type of symmetry operations, and this is C3 type. There are 2 different operations in this column, rotating 120 degrees, rotating 240 degrees, and also over here it's one type of symmetry operations. There are actually 3 different operations, alright, because we have 3 different C2 axes, and you can do a rotation about each of the 3 rotation axes. So that's why we have 1, 2, 3, 1, 2, 3 over there on top, and then we do the multiplication. So this times 1, this times 2, this times 3, this times 1, this times 2, this times 3, and I can click this, G14 times G1, and this is B14 times B1, D14 times D1, etc. Now we have another product here. Over here we take the number of symmetry operations in each type into account. And now we multiply these numbers by the characters of each symmetry. Alright, we have 6 different symmetry. And then we have this multiplied by the 6 characters in the row of A1 prime. We multiply this 6 numbers with the 6 characters in the row of A2 prime. I'm going to double click this to show you one example, $15. So this number times B9. And where's B9? B9 is simply this character in the row of E double prime. And then we have this 6 numbers times this 6 numbers. Alright, so if I click here, you can see it's $15, this one times E9. And this is $15, this number times E4. Because over here we're looking at A1 prime. So let's take a look at A1 prime over here. And we have this done. Now we sum up this 6 numbers for A1 prime. We get 24. We sum up this 6 numbers for A2 prime. We get 12. And similarly for E prime, we have the sum. For E double prime, we have the sum. And now we have the sum divided by the order of the D3h point group, which is 12. Again, this 12 is the number of symmetry operations here. Alright, so if you sum up the numbers of symmetry operations, it's actually 12. And also you can square all those numbers under the identity operation. If you square them, you get 11414. You sum it up, you also get 12, which is the order of the D3h point group. And then we do a division here. The sum divided by order, we get 2, and then 1, and 3, and 0, and 2, and 2. I'll make sure you have integers here. If not, there's something wrong, because they are the number of motions this structure may have. So when we have 5 atoms, each atom has 3 coordinates, x, y, and z, independent coordinates. And then we have 15 independent coordinates. If you have 15 independent coordinates, you have 15 motions. And over here we have 15 motions. 2 A1 prime and 1 A2 prime. Over here, 3 pairs of E prime. 3 pairs of E prime, because E means doubly degenerate here. And then we have 2 A2 double prime and 2 E double prime. Alright, we do not have A1 double prime. So we have 50 motions here. You need to count this 2 times, you need to count this 2 times, and then you get 15. Why do we have -1 here, -1 here, -1 here, -1 here? Because all this belongs to the translations and rotations. How do we find translations? X, Y, and Z are translations. So they belong to E prime and A2 double prime, irreducible representations. And then we have R sub Z, that's the rotation about the Z-axis. It has a A2 prime symmetry. And then we have doubly degenerate motions, R sub X, R sub Y, this is E double prime. E double prime symmetry, or E double prime irreducible representation, a concept in linear algebra. Alright, so that's pretty much it. What's the difference between prime and double prime? You probably can see over here you get 1, 1, 2. Over here you get -1, -1, -2. Over here you have 1, 1, -1. Over here you have -1, -1, 1. So you can use the character tables to understand the difference between the symbols. And between 1 and 2, you can see these two they have opposite signs. 1, 2, they have opposite signs. Alright, now let's get to the end. We need to subtract the rotations and translations. Now we have the vibrational modes. We should have a total of 9 vibrational modes, because we're going to do 5 atoms times 3, we get 15, and then minus 6. You minus 3 translation, minus 3 rotation, you get 9. So we have 9 here. So 1, 2, over here 2 pairs, alright, and then 1, and then over here 1 pair. So 1, 2, plus 4, that's 6, 7, plus 2, 9. Alright. Among the 9 vibrational modes, you have 2A1 prime, 2E double prime, E single prime, 1A2 double prime, and then 1E double prime. And I usually use a computational chemistry software to calculate the vibrational modes for a molecule like this, and then assign the irreducible representations to those vibrational modes. And also you can just look at this characters. So for example, if you have E prime, and you know it's gonna be infrared active, because over here you can see XY, they correspond to the dipoles in infrared, and Z, this is infrared active. And also you can determine if vibration is Raman active or not. So over here you look at the elements in the polarizability matrix of the system. So you have this, this, and this. Those are the elements in the Raman spectrum. Alright, so A1 prime is Raman active, E prime Raman active, and E double prime is also Raman active. Alright, and not only that, X, Y, and Z correspond to the p orbitals. This correspond to d orbitals. And over here you have cubic functions. They correspond to f functions, and you might realize they are related to atomic orbitals, and we can use this character table to analyze molecular orbitals. And molecular orbitals are simply interaction between atomic orbitals. Alright, so that's about it for this structure with 5 identical atoms. What if you have another atom right in the center? And over here there's another spreadsheet titled D3h AX5. So if you put another atom right at the center of this structure, I'm gonna label that A. Alright, right at the center. So the only thing you need to do is, if you are interested in the vibrational modes, the only thing you need to do is you look at this row, the number of atoms that remain in original positions. Just add 1 to every single number here, right? Because the center atom never moves. The center atom of a structure never moves after you do any symmetry operation. So just, it's gonna be 6, 3, 2, 4, 1, 4. All right, 6, 3, 2, 4, 1, 4. So over here you can see 6, 3, 2, 4, 1, 4. And in the end you'll get the vibration modes as well. Alright, it's just this will be more than the previous D3h. Alright, and you will have one more E prime and one more A2 double prime. They correspond to XYZ motion and Z motion from the central atom. From the central atom you have additional characters. Alright, you have additional characters. That's it. Again, you can download this Excel spreadsheet by just clicking this inbin-ge.com. That's my website. Or you can just simply Google PCAM CW. I'm gonna Google PCAM after this Wikipedia, and usually it's on the first page. So over here, this is my website, PCAM. But if you search for PCAM CW, you will see the first link pointing to this web page, And again, I have a bunch of files. This is the Open PChem textbook, and we have building physical chemistry from scratch. And down there we have molecular symmetry, including this spreadsheet.